So may I just ask a question? Where did November go? We're almost 2/3 of the way through the month. Where did November go? It felt like it was the beginning of November yesterday, and now all of a sudden it's the 18th, and that makes no sense to my brain. All right. So hopefully you pulled up the e-learning slides for logic and reasoning. They may not be a perfect overlap because there are some things that I kind of want to show in class rather than on screen. So we're going to talk about logic and reasoning today. So for some of you, this is going to be probably the hardest section to really wrap your head around because the principles of logic and reasoning are very, very different from how we informally reason and things like that. So actual formal logic is very, very different from informal logic. And if you want to get a handle on what formal logic looks like, Dr. Roundtree teaches a class in logic. Has anybody taken it? It's pretty hardcore. Just formal logic in general is really interesting to learn about. So I'm sorry, I'm about to do the thing I always do because I'm Dr. Gilchrist. Yeah, I was a philosophy minor. I was required to have a minor at my college, and I ended up picking philosophy because one of my first classes was an intro to philosophy class, and I liked it so much that I'm like, you know, I could minor in this. And one of the requirements was that I was supposed to take a logic class. And honestly, folks, it is one of the best classes that I took. It's probably been one of the most useful classes that I took. If you are interested in things like computer programming or algorithms, logic and reasoning is actually a very helpful class. I do a lot of programming in my work when I make experiments. Logic and reasoning has been one of the most beneficial classes that I've ever had. So we are going to talk about logic and reasoning, and we have to start by talking about a difference between what we call deductive reasoning and inductive reasoning. So deductive reasoning is basically drawing a valid conclusion from a set of premises. Now, oftentimes these are going to utilize formal logic. And unless you are taking a class that uses formal logic, this is not something that you typically do. We're going to talk a little bit about how informal reasoning looks very, very different from using formal logic. Here we go. Okay, is everybody good? All right. So we are going to talk a little bit more about this later, but we're also going to spend a lot of time talking about inductive reasoning first. So inductive reasoning is very, very different from deductive reasoning. So deductive reasoning starts with premises and ends with a conclusion drawn from those premises. But most of our reasoning is actually going to be what is called inductive reasoning. Now, deductive reasoning is all about drawing starting with something specific and then making a very general conclusion. So we have these specific premises and we create a general conclusion based off of those premises. Inductive reasoning is different. We start with a general idea and we move to something more specific. So an example of this is theory testing and hypothesis testing. So from a very general theory, we develop a specific set of expectations or conclusions. So for example, if I have the theory that all Chinese food is too spicy for me, I'm going to draw the specific conclusion that I will probably not like Kung Pao chicken, a very specific instance, because all Chinese food is spicy. So I argue from a general conclusion to a specific premise. And it turns out that most of our reasoning is very, very inductive. We have a lot of general ideas of how we think people behave, how the world works. And so we're often arguing or thinking about these general ideas and then applying them in very, very specific terms. Now, nowhere does this come into play more than when we do something called hypothesis testing. So I am specifically talking about any sort of hypothesis. So I'm not just including researchers like me who do experiments and come up with a hypothesis. So a hypothesis, we have an idea of what data or what something should look like based on an overarching general principle. So we have an idea of how the world works and we want to test it and see if the data fits with that general conclusion. So how should we actually test a hypothesis? So a lot of our understanding of how we should scientifically test comes from the work of the philosopher Karl Popper. Now, Popper believed that when we are trying to test a hypothesis, we should not be seeking to confirm that our hypothesis is correct. We should not seek to confirm it. We should seek to prove it false or to confirm that it's false. So we should focus on instances that would make the hypothesis false rather than focusing on confirmation, which is basically obtaining evidence that confirms that your hypothesis is correct. So I want to do something. I want to talk a little bit about this in particular. So I'll let you write this down and then we're going to try something. And I think this is something that you can do if you're zooming in and you want to chat. And I think you can do this here if you're in class as well. So this is something that we all can do. Okay, so let me see. Oh. Now, on the other hand, falsification is basically attempting to falsify a hypothesis through tests. And for those of you that are thinking about taking research methods or you are taking research methods, you know that by and large, when we look at data, we are attempting to falsify a hypothesis. We are not necessarily seeking to confirm, or at least that's how things should be. We'll talk about how actual research scientists use hypothesis testing and whether or not they engage in falsification in a minute. It's a little bit more complex than you think. All right, you good? Okay, so we're going to try something. I am going to present you with a sequence of 3 digits, that have been organized according to a particular rule. Now, I know what that rule is. I don't think you know what that rule is. So here's what I'd like you to do. I would like you to generate 3 numbers, and I'd like you to provide a reason or your rule for the set. And actually, you know what? Get rid of the rule. Here's what I'll do instead. You'll probably have an idea of a rule in mind when you make your sequence. Tell me what that sequence is. I will tell you if it fits with my rule. And if you think you know what the rule is, you don't have to tell me what you think the rule is, but if you think you know what the rule is, tell me. So it's kind of like a Wheel of Fortune. If you think you know what the answer is, just shout it out and let me know. So I'm going to go ahead and write this on the board. I'm going to stop sharing the screen, and I will pull up the chat so that we can see. All right, so I'm going to go close that, and I'm going to pull up the chat. So here is my sequence, and this sequence is based on a rule that only I know. So you need to figure out what the rule is based on different sequences of digits. So here's the sequence. So for those who cannot see, I went and moved the camera just a little bit, a little more. There we go. So our sequence of digits is 2, 4, 6. So now generate a sequence. I will tell you if it fits the rule. And if you think you know what the rule is, type it in the chat. So can somebody give me a number sequence? Robin.
2 plus 10.
Huh?
Is it like an
You have to give me 3 numbers.
3 other numbers?
Yeah, you have to give me 3 numbers. So Maya said 20, 22, 24. That fits my rule.
Oh, I gave you the formula.
Oh, well, I didn't hear it.
Yeah,
So
we do 8, 10, and 12. I just did 2.
8, 10, and 12?
Yeah.
That fits the rule. And what do you think the rule is, Robin?
2 plus n.
2 plus n, so n plus 2. That is not the rule. Geneva says 21, 22, 23. That does fit my rule. Anybody else? Any ideas? Successive numbers. Not exactly.
Like
So
they're
I'm gonna
higher than the
say
previous number.
no. So 20 or 21, 22, 23 fits the rule, but successive numbers is not correct.
Like it's just numbers that get higher.
Oh, well, it should. I can't do anything about the mic. I'm not the one who installed it. Can you hear me now? I'm loud enough.
Can you hear me?
Oh, okay. That's all right. That's okay. You can type in the chat. I'm fine with that. If your mic doesn't work, that'll work. Numbers that get higher. There you go. There you go. So technically, here is something else that could have fit the rule. 5, 100, 1,000. That technically fits the rule. Oh, okay. So when I hear successive, I hear 1, 2, 3. Oh, you know why? I bet I know why I can't hear, because the volume's not on. The volume might not be on. That might be why. I don't pretend to understand it. So the rule is basically any number that gets higher. When I hear the numbers, when I hear succession, I mean one right after the other in sequence. So 1, 2, 3 are successive numbers. So sorry that I kind of misunderstood you. So here's what's kind of interesting. So all of you that gave me a sequence, so Maya gave me a sequence, and Geneva gave me a sequence, and Robin gave me a sequence, you all picked sequences that sought to confirm your answer. You did not give me a sequence that did not fit with your rule. So if you thought it was increasing by 2, what you should have done, remember that we're not as rational as we'd like to be, What you probably should have done is given me numbers that didn't increase by 2. And if it turned out that that fit the rule, that meant that your original rule was incorrect. You learn a lot more from what doesn't fit the sequence than what does. And so I find that kind of interesting that even here, when asked to generate sequences, you all picked sequences that fit the rule. You didn't generate a sequence that went against the rule that you had. So this is Wason's 2, 4, 6 task. People show confirmation bias. They select items that fit, they give list items that basically seek to confirm the rule that they have in their mind. They fail to use falsification. And they largely generate numbers that confirm the hypothesis about the rule. So congratulations, we all engage in confirmation bias, and I am not immune to this. When I was given the 246 class or task in my cognitive psychology class, I did the exact same thing. So I am not immune. It's not like I'm like, I never do this. I do this all the time. So performance should actually improve. You would think that performance should improve when people have to engage in falsification. So people have actually tried the Wason task with directions to actually pick a sequence that disconfirms their hypothesis. So even when people are engaged and are basically told to engage in falsification, the results of how well this works is mixed. We seek to confirm. Seeking to falsify seems to not really occur to us, even when we're encouraged to. All right. So how do you get people to discover the rule? Poltiek in 1996, when you get instructions to confirm, that when people actually get explicit instructions to try to confirm with different tests, it actually increases the number of negative tests. So people generate rules and then they're told, hey, that's not correct. And notice that you didn't necessarily need to engage in falsification. You generated a sequence and then based on my feedback, you learned more about the rule. So when people get instructions to confirm, this actually increases the number of sequences that people generate that go negative, that don't fit the rule. And when people do this, they're able to learn more quickly what the rule is. Now, numbers that increase is a really vague, very general rule. So what if we made the rule more specific? So numbers that increase by 2 or numbers that increase by 1. Clayman and Ha have actually found that when the rule is more specific, that actually helps people discover the rule more quickly. A general rule is a lot harder to parse. If we mention 2 examples that fit the rule rather than just 1, That also seems to provide a benefit, as Cherubini and colleagues found in 2005. So all of these things actually help people discover the rule a bit more quickly. So how does, oh, do y'all need me to go back? Okay, so how do scientists test this? So Meitroff and colleagues actually tried to figure this out because science is all about hypothesis testing. And Karl Popper himself was a philosopher of science and said that, well, we should seek to falsify. Scientists have been trained in the scientific method and they know the power of falsification. And yet, Meitroff in 1974 actually found that scientists spend more time confirming their hypotheses, not falsifying them. Having said that, though, they are prone to disconfirming other hypotheses or falsifying others' hypotheses, as long as they're not their own. They're happy to sink somebody else's hypothesis, but they're less likely to abandon their own. Now, part of this happens because of the way that we approach these things. So a lot of this happens because of how we approach this. So one of the things that you kind of have to know about science research, remember that most people who are working in a scientific field have spent a lot of time, and especially if they're advanced in their careers, like if we're talking if they're in their 50s, 60s, and 70s, they have spent a lot of time creating different theories, coming up with different ideas. And because of that, that's a good chunk of their life's work. Their ability to get funding, their ability to get published is all based on the idea that their theory works. Because of that, there's a lot tied into their livelihood and their well-being and their work is all tied into whether or not this theory or this hypothesis works. And if it doesn't, well, they're going to have to start all over again. And unfortunately, the system does not necessarily reward innovation. The system rewards previous evidence. So you can't just propose a new hypothesis that nobody's done research on before. It has to already be kind of established. So the system does not necessarily reward innovation and novelty the way it should. And because of that, you're going to see people engaging in a lot more confirmation than falsification. There's a greater commitment. They have more of their livelihood tied into keeping that hypothesis positive and not having to falsify it. And if they do find disconfirming evidence, they're usually going to attribute it to measurement error or procedure error. I have had people point blank tell me to my face that the reason that I couldn't replicate their findings were because I did it wrong. I'm sorry that I didn't give the right instructions. And frankly, this is my belief. If you getting a particular finding depends on something as subtle as how you give instructions, either that effect is not very large and does not pop up in the general population, or it's probably not a real effect to begin with. Sorry, I'm a little harsh, but you can kind of see how much researchers who put their life's work into this really cling to their ideas. They have to. The system is built for that. Maybe we need a new system. Okay, so should falsification be a goal for scientists? Now, Popper makes the assumption that research can decisively rule out a hypothesis. So as soon as I get one negative finding, So if I believe, for example, that false memories are not real, I should just have one study that doesn't show false memory, and that should be enough, right? That's not true. Falsification of a theory or a hypothesis usually requires more than data from one study. It needs to be a repeated pattern. And one of the things that's actually interesting, so when you look at how scientists engage in inductive reasoning with hypothesis testing compared to college students that have to do this in a simulation, we do find that the scientists are far more committed to confirmation than the simulated research scientists. But simulated researchers that are doing work in teams are often more open to new ideas, including falsification. So now we're going to talk about deductive reasoning. And this is where it gets a little bit more complicated. So deductive reasoning is often going to be based on some logical operators via conditional reasoning. So conditional reasoning will often include statements such as if, or possibly or. So that includes statements like or, and, if, then, or if, and only if. So we have a variety of different logical operators. So for example, this is from your textbook. If it rained, the road is wet. So this is a proposition that is either going to be true or it's going to be false. So now here's where deductive reasoning gets a little bit difficult to parse. So when we talk about something being valid informally, so when we say that's a valid point, we're typically using the word reasonable. So valid will often mean reasonable or understandable. This word, valid, has very different connotations in deductive reasoning. So when we talk about the validity of an argument, we are not necessarily talking about how reasonable it is per se. Validity is basically the idea that we're going to ask if the argument is valid. And what do we mean by the argument being valid? First of all, we assume that the premises are true. We have to assume that the premises are true. And the conclusion must naturally follow from the premises. So here's what this implies. Validity has nothing to do with the content of the argument, and it has everything to do with the argument's form. So it has nothing to do with the content. It has to do with the form that the argument takes. So what this means is there are arguments out there that do not sound logical, but they are valid because they are in a proper form. So logical validity in deductive reasoning has nothing to do with the content. So I can technically argue that unicorns exist or that ghosts exist, but the content doesn't matter. It's the argument that matters. It is the form that matters. And some people have some difficulty wrapping their heads around that. So one of the first arguments that we are going to talk about is what is referred to as modus ponens. So I'm going to go ahead and explain what this means, and I am going to annotate, and I'm going to draw this really badly. Actually, I will use text. So this little item right here is, I'm going to put this right here. So this little argument has a weird little arrow to it. Here's what it basically means. If P, then Q. So that's what the first part of the argument means. This little P arrow Q means if P, then Q. So that's the first statement of the argument. P, so P, and then this little line with the Q underneath means, so the little line means therefore Q. So here, it doesn't matter what you put in the argument. So it's if P, then Q, P, therefore Q. So your book gives this example. This one basically says, if it rained, so I'm going to go a little differently. If it rained, then the road must be wet. So you can fill in P with anything. So I'm going to pick if it rained. So that's my P. My Q is the road must be wet. So if it rained, then the road must be wet. It rained, therefore the road must be wet. Now, is that a case where if we assume that both of those premises are true, that the conclusion naturally follows? Actually, it does. Modus ponens is a valid logical form. So let me go ahead and put that here so that you know this. Oh, no, I want text. Text. So here's the thing. As long as you're following modus ponens, you can fill anything in P and Q and make it a valid argument. Does anybody want to try that? You can make this say anything and it's technically logically valid because the conclusion naturally follows from the premises if it is assumed to be true, if both of these are assumed to be true. So fill in the P and the Q for me, somebody. Let's have some fun with this. We can make anything we want, and it's a logically valid argument because the only thing that matters is the form. I'm very excited about this, and some of you are like, my head's going to explode. I didn't mean you. I meant anybody. Anybody want to try this? P can be anything and Q can be anything. Okay, so if pigs fly, then dogs have beaks. Pigs fly, therefore dogs have beaks. Yeah, and that's totally a logically valid argument. Now, none of those things are actually true, but if we assume that these two statements are true because these are our premises, the conclusion, therefore dogs have beaks, follows naturally from these premises. So the form is what matters. Okay, so I'm going to clear, Ah, no. I get too excited about my annotations. Ah, and I did it again. Undo. Okay, close. All right, so that's our first logical form. Now we're going to talk about another one that is valid. This is what is called modus tollens. So I'm going to write this down so you know. And again, we're going to use these special symbols. So I'm going to put them right here. This is in a slightly different form. So this says if P, then Q. Okay, now here's where it gets interesting. This is a special signifier that says not Q. So this says not Q. So these are our two premises. If P, then Q. Not Q, therefore not P. So that little weird triangle with the dots is a therefore, not P. So this is another valid argument. So here's an example. So again, you can fill these in with anything and it is still technically a valid logical form. So if it is Christmas, then it must be December. It is not December, therefore it is not Christmas. And that kind of logically follows from the premises if we assume that they're true. So does anybody want to try to fill this one in? I'll try another one. If Vera is here, then my Mountain Dew is missing. My Mountain Dew is not missing, therefore Vera is not here. Okay, so now we're going to look at a few other examples. So let me go ahead and clear these annotations. So now we're going to look at some different logical forms. Again, so we're going to talk about four major forms. So we've talked about modus ponens, which is valid. We've talked about modus tollens, which is also valid. Now we're going to talk about something called affirmation of the consequent. So this is a little bit of terminology for you. So if I have this, so if I have an if P, then Q statement, so this, let me go ahead and draw this. So if P, then Q, I'm drawing on an iPad. Apparently my skills look much worse when I'm working with a mouse. So this, when we have if P, then Q, so Q is what is called our consequent. This is referred to, so the P is referred to as the antecedent. So this is going to come into play when we talk about these next two argument forms. So we have affirmation of the consequent, and we have the antecedent. So here is an example of affirmation of the consequent. So this is while watching Intervention. All crackheads love Mountain Dew. Hey, I love Mountain Dew. Exactly. So this is technically an affirmation of the consequent. So let's kind of write out this argument in a more deductive form. So if you are a crackhead, you love Mountain Dew. So that's the first statement. So this is our antecedent. You are a crackhead. This is the consequent. You love Mountain Dew. You love Mountain Dew. So this would be what's called affirming the consequent. We're saying, yes, the consequent is true. Therefore, you are a crackhead. This is one of the weirdest arguments I've ever pulled up. So, is this a valid argument? It's actually not. This is not a valid argument, and here's why. If we are assuming that all crackheads love Mountain Dew, if you love Mountain Dew, so we're affirming the consequent, does it necessarily follow that you are a crackhead? No. And because that does not follow from this, the conclusion that you must be a crackhead does not naturally follow from the premises. We're only talking about crackhead, specifically about crackheads. You can love Mountain Dew and affirm the consequent without being a crackhead. This is a more specific instance. This is looking at a very specific group of people. And thus, because this conclusion does not follow from the premises, affirmation of the consequent is not a logically valid form. People think it's valid. It is not valid. So don't feel bad if you thought it was valid. Deductive reasoning is really hard. Talking about the validity of arguments is hard. So here's my promise to you, if you're taking the 4th exam, I might ask you about some of these logical arguments, but here's the catch. I will never ask you why something is valid. You simply need to know that certain logical forms are valid and other ones are not. You do not have to understand why. You just need to know that affirmation of the consequent is not valid. Yes?
But can an argument be valid and not sound?
Oh yeah, and that's part of the reason why it's easy to get tripped up by these, because we spend, when we do informal reasoning, we focus on the content. And it's hard not to look at that content and be like, that makes sense.
But it's not sound, but it's valid.
No, it's valid, but it's valid. It is a valid form, but it doesn't seem valid. Or it's not a valid form. Sorry, I'm getting confused. Let me try that again. It's not a valid form, but the reasoning, at least informally, makes sense. But this is formal reasoning, and this is a very different ball game. I am less concerned about why something is valid, and I'm more just concerned that you know it. Just know that this is not valid. Now, here's a better example that can help you understand why certain arguments are not valid. Affirmation of the consequent is a really hard one because it seems like it would make sense. So here's a better example that has nothing to do with Mountain Dew. If you have an apple, it must be green. You have something green, therefore it must be an apple. Does that make any sense? Like, does that follow from the premises? Not at all. You can have a lot of green things that are not apples. So does that one that I just gave you, if you have an apple, it must be green. You have something green, therefore it must be an apple. Does that make more, does the fact that it's not valid show up a little bit more in that instance? Good. Good. So the idea is you can plug anything into this form and it should be very easy to see why it's not valid. But because informal reasoning is more focused on the content and this content makes sense to us, we're going to believe that affirmation of the consequent is valid and it's not. Now, here's an easier way to see an invalid argument. We're going to talk about something called the denial of the antecedent. So again, I will kind of put this in a form that will help. So if P, if comma P, if P, then Q. So remember that P, oh, no, go away. I want to move you. I can't move it. Okay. So if P, then Q. P is our antecedent. Q is our consequent. So denial of the antecedent basically the denial of the antecedent basically takes a form like this. If you are a ski instructor, then you have a job. You are not a ski instructor. Therefore, you do not have a job. Can you see that this is not a valid argument? Yeah, you can think of a lot of counterexamples of people who have jobs and are clearly not skiing instructors. So this is a case of the denial of the antecedent. So it's if P, you're a ski instructor, then Q. Not P, therefore not Q. That is not a valid argument. This premise does not tell us that only ski instructors have jobs. So part of the reason that people get kind of tripped up by these invalid forms is that we assume that the if is actually if and only if. So when we hear if you are a ski instructor, then you have a job, we're assuming that only ski instructors have jobs. That if becomes an if and only if. But there are a lot of people out there with jobs that are not ski instructors. And people are actually really good at recognizing that denial of the antecedent is not valid. We have a harder time with affirmation of the consequent. Now, likewise, we have an easier time believing that modus ponens is valid. We have a harder time believing that modus tollens is valid. Okay. All right, folks, so that is all we have for today. We will talk about what people think about these arguments, and we'll talk a little bit about syllogistic reasoning, which is always the part that I don't like. So have a wonderful day. I will see you here on Friday. Take care of yourselves, and I will see y'all later. Bye. I told you to end the meeting. End the meeting. Oh, I got to stop share first and then end the meeting. Goodbye.